rotation about a fixed axis. Look at this figure. Consider this rigid body in the xy plane and fixed axis perpendicular to this plane, so it is in the z-axis. For rigid body planar motion, rotation is limited within the xy plane, although it looks like rotation is only about a fixed point in this plane. In reality, rotation occurs about the z-axis that passes through this point and is perpendicular to the xy plane. Therefore, this is known as rotation about a fixed axis. During rotation about a fixed axis for any point in this rigid body, its path of motion is always circular, with radius being the perpendicular distance from this point to the axis of rotation. We can draw an arbitrary line that is within an arbitrary cross-section which is perpendicular to the axis of symmetry, and after some time it has rotated to a new position compared to its original position. It has rotated by angle theta. And theta is known as the angular position for this rigid body during rotation, and it has the unit of radian. And we know that the time derivative of angular position is angular velocity, which equals d theta dt, and it has the unit of radian per second. An angular acceleration alpha is defined as the time derivative of angular velocity d omega over dt, or the second time derivative of angular position theta. It has a unit of radian per second squared. If we cancel out dt from these two equations, again we get the third kinematic equation, alpha d theta equal omega d omega. As you remember, we learned about the three basic kinematic equations for linear motion in chapter 13. And now we learn the three basic kinematic equations for angular motion, which have very similar format as a linear motion. Similarly, we have these three equations that apply for linear motion with constant acceleration. Also, we can derive these three equations that apply for angular motion with constant angular acceleration. Okay, how we find the angular velocity of the rigid body? Look at this figure. When the rigid body undergoes rotation about a fixed axis, an axis that passes through point O and is perpendicular to the xy plane, a point F on this rigid body undergoes curvilinear motion following a circular path. The position of point F measured from the fixed axis is position vector r, and its linear velocity as we learned before. It is always tangent to the path, and the speed scalar v equals to ds dt. And since s is the length of the arc, which equal to r times theta. R here, the r here is the perpendicular distance of point F from this fixed axis, and theta is the angular position of this rigid body, and therefore V equals r times d theta dt, and d theta dt is the angular velocity of the rigid body and shown by omega. So the velocity in the angular velocity of the rigid body find by this equation. V equals R times omega. In this slide, I'm talking about how we find angular acceleration of the rigid body. Again, look at this figure. The linear acceleration of point F equals to dv dt. And since we just derived that the linear velocity v as a vector equals to the cross product of omega and r. Therefore, the linear acceleration equals to the omega dt cross r plus omega cross dr dt. By applying the product rule from the calculus and this term, d omega dt is the definition of the angular acceleration alpha. And also this term, dr dt, is once again the linear velocity and it's equal to omega cross r. Therefore, the acceleration after simplification becomes the cross product of alpha and r minus r omega square. R alpha or alpha cross r has the same sense of direction as the linear velocity. Therefore, it is the tangent acceleration as we learned about before. And omega square r has the opposite direction as the position vector r. Therefore, it points to the normal direction and it is the normal acceleration component. Let's look at one example. Gear A of the winch turned gear B and raising the hook edge. Gear A starts from rest at time 0 and its clockwise angular acceleration is given as a function of time by 0.2 times t. What is the upward velocity of the hook and what vertical distance has it risen at time 10 seconds? First of all, we have to draw the free body diagram. At their point of contact, the gears have the same tangent component of acceleration. The tangential component of acceleration equals the product of the radial distance from the axis of rotation and the angular acceleration. So we find the alpha b from this equation. After that, we have to determine the angular velocity of b. By integrating the alpha b, we can determine the angular velocity of gear B as a function of the time. And the omega b is equal 0.025 t squared. And the next step, by integrating the omega b, we can determine the angle through which in gear B has turned as a function of the time, and we find the theta b. Okay, now again we draw this one. The velocity of the hook is equal to the velocity of the gear at 0.1. So we find the velocity of the hook. The velocity of hook is 0.25 meters per second. Now, the amount of cable wound around the drum at time 10 seconds is the product of theta b and the radius of the drum, that is equal to the vertical distance it has risen. So the total distance has it risen is 0.833 meters. Thank you for watching.